The advanced air mobility industry is currently working to produce novel aircraft ranging from air taxis to autonomous cargo drones. And all of those designs will require extensive testing, which is why NASA is working to give them a head start by studying a special kind of model wing. The wing is a scale model of a design used in a type of aircraft called a tiltwing, which can swing its wing and rotors from vertical to horizontal. This allows the aircraft to take off, hover, and land like a helicopter, or fly like a fixed-wing airplane. This design enables versatility in a range of operating environments. Several companies are working on tiltwings, but NASA's research into the scale wing will also impact nearly all types of advanced air mobility aircraft designs. NASA research supporting advanced air mobility demonstrates the agency's commitment to supporting this rapidly growing industry, said Brandon Litherland, principal investigator for the test at NASA's Langley Research Center in Hampton, Virginia. Tool improvements in these areas will greatly improve our ability to accurately predict the performance of new advanced air mobility aircraft, which supports the adoption of promising designs. Gaining confidence through testing ensures we can identify safe operating conditions for these new aircraft. In May and June, NASA tested a 7-foot wing model with multiple propellers in the 22-foot subsonic wind tunnel at Langley. The model is a semi-span, or the right half of a complete wing. It was designed to ensure the model would fit inside the wind tunnel. And because of the symmetry of the wing, data gathered from one side can be extrapolated to the other. The semi-span features 2 flaps near the wing root or leading edge and 4 at the wingtip or trailing edge. During the tests, the flaps were set at 10 degrees for all of the test points. The flaps are designed to delay flow separation over the wing, which improves lift and efficiency, but the team wasn't focused on collecting data about the flaps during this round of tests. Understanding how multiple propellers and the wing interact under various speeds and conditions provides valuable insight for the advanced air mobility industry. This information supports improved aircraft designs and enhances the analysis tools used to assess the safety of future designs. This work is managed by the Revolutionary Vertical Lift Technology Project under NASA's Advanced Air Vehicles program in support of NASA's Advanced Air Mobility mission, which seeks to deliver data to guide the industry's development of electric air taxis and drones. This tiltwing test provides a unique database to validate the next generation of design tools for use by the broader advanced air mobility community, said Norm Schaffler, the test director, based at Langley. Having design tools validated for a broad range of aircraft will accelerate future design cycles and enable informed decisions about aerodynamic and acoustic performance. During the tests, the model was mounted on a turntable so the team could rotate it to various angles to simulate different flight conditions. Researchers also could change the relative positions of the propellers while the wing was rotating to see how the adjustments impacted the overall model. The team gathered data at several speeds to represent different flight scenarios. The test article had several oil total pressure probes installed to visualize the flow over the wing and propellers. The team also recorded high-speed video to supplement the data. The wing is outfitted with over 700 sensors designed to measure pressure distribution, along with several other types of tools to help researchers collect data from the wing and propeller interactions. To measure the forces acting on the wing model, the wing is mounted on special sting and trunnion-type load cells that allow engineers to measure the force and moment on the model. In addition, there are sensors in each motor propeller hub to measure the forces acting on the components independently. These tests build on previous NASA research to provide data for improving computational fluid dynamics prediction tools. These tools allow engineers to virtually test designs before building a physical prototype, which can save time and money. More efficient and accurate computer models also reduce the number of wind tunnel tests needed, which have traditionally been expensive and time-consuming. By increasing the accuracy of computer models, engineers can better predict how a design will perform, reducing the need for costly and time-consuming redesigns. In 2019, NASA conducted tests in the 14x20-foot subsonic wind tunnel on a single propeller and a wing with one propeller mounted on the wing. Those tests provided a baseline for the current tests. The additional propellers on the new model allowed the team to gather more comprehensive data about complex interactions between the wing and propellers, particularly the interaction between the wing and the two center propellers. When the test article was in the horizontal position, the propellers generated thrust in a direction parallel to the tunnel floor. As the angle of attack increased, flow features changed significantly as seen through the oil flow visualization. The flow transitioned from attached and laminar to detached and turbulent. At higher angles, the flow remained attached to the top surface of the wing and became highly three-dimensional due to the influence of the downgoing propellers. In the vertical configuration, the propellers generate thrust perpendicular to the plane of the wing, which resulted in a different flow pattern than when the wing was in the horizontal position. In this orientation, the upgoing propellers pushed the flow toward the wing, resulting in an adverse pressure gradient on the upper surface. The propellers were generating thrust in the positive x direction or the direction of the oncoming flow. When the wing was in the horizontal position, the propellers were generating thrust in the negative x direction or opposite the direction of the oncoming flow. As part of these tests, NASA is validating computational fluid dynamics tools using the data from the tests in the wind tunnel. One tool being used is the Overset Grid, Chimera and Adaptive Mesh Refinement, or AUM, for CFD simulations. The Overset Grid Chimera and Adaptive Mesh Refinement methodology is an advanced numerical technique for modeling complex aerospace geometries. The approach offers an efficient means of simulating the flow around multiple lifting surfaces such as wings and propellers by allowing for independent refinement of the computational mesh in different regions. This flexibility enables more accurate predictions of flow behavior in areas of high aerodynamic complexity, such as the region between the wing and propellers, where traditional CFD methods often struggle. Another tool being validated is the Unified Approach for Large Eddy Simulation, or ALS. ALS is a cutting-edge computational fluid dynamics method specifically designed to tackle the challenges of simulating turbulent flows in aerospace applications. Its effectiveness lies in its ability to model the complex interplay of small-scale turbulent motions, which is crucial for understanding the behavior of flows around aircraft components like propellers and wings. Unlike traditional large eddy simulation methods, ALS offers an efficient and accurate representation of turbulence, making it a powerful tool for analyzing the intricate flow patterns around advanced air mobility aircraft. The data collected during the tests will be made publicly available to the advanced air mobility industry. NASA has a long history of supporting the aerospace industry through fundamental research. For example, NASA's Quiet Spike program in the 1970s led to significant advancements in rotorcraft technology, laying the foundation for modern tiltrotor aircraft like the Bell Boeing V-22 Osprey. Similarly, NASA's research on supersonic and hypersonic flight has enabled significant progress in the development of new aircraft designs. Today, NASA continues to invest in research to support the development of advanced air mobility, including vertical takeoff and landing vehicles, hybrid air vehicles, and other innovative concepts. NASA's expertise in aerospace research and testing capabilities are instrumental in advancing the state-of-the-art for these technologies.